Going to look at this thing called vector projections, which actually we have already seen without you knowing. Okay? You see, when we break a vector into its components, basically we're saying it's a projection of the vector onto, now we've looked at it horizontally and vertically, so we're saying on the x-axis or on the y-axis. So here is an example of a vector. Its magnitude is 2. It makes an angle of 30 degrees with the x-axis. We could say, hey, I've projected this vector onto the x-axis, and that gives me the horizontal component of that vector. Turns out to be a little bit of trigger, we can work it out. Its length would be the square root of 3. That'd be root 3i. And then we could do the same on the y-axis. We could project over to the y-axis, and that one would have a magnitude of 1. That would just be the unit vector j. So we have done these things without knowing it. The overall vector, root 3i plus j. That's it. Horizontal and vertical, very convenient, because we think of things horizontally and vertically, but there's no reason why we have to project that way. We can project one vector onto any other vector we like. So here we go. I've got two vectors there, and I'm going to project u onto the vector v. So how do we do it? Well, it's like getting a light, if you like, behind the vector that you're projecting on and imagining what the shadow would be on the new vector. So what we do is we drop perpendiculars to the other vector, and it will create a new vector on there. Then we have to calculate the length of the shadow, if you like. Again, I can create a right angle triangle there. That angle, whatever it is, theta, and a bit of trig. It would be whatever the magnitude of u is times the cosine of that angle. That would be the length of the shadow. Then I just multiply it by the unit vector in the direction of v. I'm not going to change the magnitude, it's the unit vector, but v gives it the direction that we're now travelling in. It would be the same as vector v. So essentially that could be our formula. If I want to project u onto v, I could find the magnitude of u, multiply it by the cosine of theta, whatever that angle happens to be, and then multiply that by the unit vector in the v direction. Well, let's take that a little bit further. What we know is that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta, where theta was the angle between the two vectors. Well, that is in fact what this theta is. If I was to continue this vector down so the two vectors meet, because these lines are parallel, it's going to be theta. So this theta we're talking about here is actually the angle between the two vectors. So the magnitude of u cos theta, remember that's going to be the magnitude of this new vector I'm projecting. If I rewrite this, I can work it out by going u dot v divided by the magnitude of v. That will get me the length of this new projected vector. And we said to give it direction, we're going to multiply that by the unit vector in the v direction. So I don't actually need to know the angle. All I need to know is what is u and what is v, and then I can work out all these other things. But I can tidy that up even more. Remember, the unit vector we said was v divided by the magnitude of v. So actually what I've got in this fraction here is the magnitude of v squared. So I just go u dot v over the magnitude of v squared times v. But there's an even easier way of remembering that, because if you recall, the magnitude of v squared is v dot v. And I just find that a heck of a lot easier to remember. u dot v over v dot v times v. There it is. So v is everywhere except for the very first thing I write down, which is what I am projecting, that vector. Everything else is v. So u dot v over v dot v times v. Now it's really tempting to say, hey, why can't I just cancel these v's? Remember, dot product is not multiplication. So division is not the inverse of the dot product. So I can't cancel a dot product, because it's not v times v on the bottom, it's v dot v. So it does not cancel with those other v's. So we leave it as u dot v over v dot v times v. A couple of notes for playing with these things. If you wanted to project lambda u onto v, then lambda is just a constant number. I can just pull that out the front and just simply do the projection of u onto v and multiply it by whatever scalar lambda happens to be. And addition works too. I can do each of those individually and then just add the results together, rather than actually working out what u plus v is and then projecting it onto a vector. Whichever way ends up being easier in the question, I guess, is what we end up doing. Let's try one. But make sure you read the question. This one is not asking for the vector. It's finding the length of the projection. The length of the projection. So that part was just the a dot b on the magnitude of b. So we no longer have the b dot b, because that was once we multiplied it by the unit vector. We're not multiplying it by that at the moment. It's just that magnitude. So let's go back to our formula. It's just this u cos theta part we're trying to find. The length of that projection. So we have a dot b in this case over the magnitude of b. So 5 times 3 plus negative 1 times 4 over square root of 3 squared plus 5 squared, 11 on 5 would be the length of that projection. Okay. Sometimes you'll see that called as the scalar projection rather than the vector projection, because we're just interested in the number. We're not interested in the direction or everything, so we call it sometimes a scalar projection. Let's do an actual projection. We're going to project u onto v. U is what we're projecting. So u dot v over v dot v times the actual vector v itself. So u times v, so 2 times negative 2, that'll be negative 4. Negative 5 times 3, that's negative 15. Over v dot v, which is the magnitude of v squared. 2 squared, or negative 2 squared, doesn't matter. Square it, it's going to be positive. So negative 2 squared plus 3 squared, but multiply it by this vector. That fraction works out to be minus 19 on 13, times by that. Wow, if I want to write it as one thing, there it is. 38 on 13i, minus 57 on 13j. Just a quick one for today. Just how we project one vector onto another one.